Okay, well, oh yeah, that's good, Mike. So yeah, thank you all for coming back from your, hopefully you had a good coffee break and are now awake, contemplative. So a lot of this is, was really well touched on by Alan's talk just before, so hopefully I can maybe go into a little bit more detail on some things. So first of all, this plot should be familiar to many people, if not from before, at least from the prior talks. So this is 5914. It's a binary black hole merger. And of course, you can make a very simple plot, and it's very clear right in the diagram that there's something here, and it's in both the LIGO-Hanford and LIGO-Livingston instruments. And, you know, as well, this is a nice plot of the binary neutron star merger. It's my sort of favorite version of this plot. But as Alan so succinctly put it, and this is the point I want to drive home, this is not how we find signals. You might be tempted to believe by looking at these plots that we actually use these to find things. We don't. They're for things like this, where it gives you something pretty to look at, and it gives you, some sort of sense of some of what the evolution is of these systems. But this isn't how we make detections. And to maybe give you an example, what do you think's in this plot? Anyone have an idea? I don't expect you to know, but certainly you're not going to be able to tell much from this one. Is there a signal there? Is that just noise? How do you know? So that's what we're going to find out. So to summarize, there's two different sort of kind of pathways we have to trying to find signals for compact binary coalescences, so binary neutron star, binary black hole, neutron star black hole mergers. And sort of put them into two groups. There's template searches. Alan covered this briefly. So this is like something where we have a good model of the kind of system we're looking for. We know what the waveform looks like, and we can use that to help us find it. Okay, there's also burst searches. These use a variety of algorithms. They look for excess power, but they may have some ability to constrict to sort of coherent excess power that has to appear in the instruments in a sort of similar morphological way. And there's a couple different categories of searches that these are different names of different pipelines and different tools that are used to do these, especially looking for compact binary coalescences. There's a burst search called CWB. There's template searches called CBC and GST-LAL. Those are the primary ones. And I'll note that I'm not going to talk today about low latency analyses, although all of these ones can be run in low latency. If you have questions on that, I'm sure we'd be happy to talk about that, and Mina might talk about that later on. Now, I just want to touch a little bit right now about CWB. So CWB is a sort of generic technique. They don't require knowledge of what the exact signal looks like, but they do put in some restrictions. In particular, they do use a kind of wavelet time frequency decomposition. And then they get from that a set of tiles. And then the trick is in how you choose those tiles and how you cluster them. And they do it in such a way that the frequency increases over time. So they are looking for at least things that increase in frequency over time. That could be something that is chirp-like. So it's not entirely uninformed, but it doesn't require knowledge about the exact evolution of a particular signal. And so that's a particularly advantaged thing if you have systems where you don't necessarily know what it exactly looks like, or you may be very hard to search for because it has physical effects we don't know how to model. And I will point out that they have the distinction of being, they are actually used in practice, and they've been quite useful. In fact, they were the first ones to see our first binary black hole merger in low latency. Now, during this talk, I'm going to talk mostly about the CBC analysis. That's one I've been involved in with developing, so I'm the most experienced to talk about. And I will touch upon some of the techniques used elsewhere, but I'm going to try to focus on this one. So, where do we begin? Well, the goal that I would like you to come away with is how to understand a plot like this. So on the x-axis here, we have something called detection statistic. And the vertical axis, we have number of events. And you can see this black curve here is background. And this orange is what we see when we actually do the analysis. And you can see that there's this very large outlier. That's 5914. And this plot tells us that it's a very significant event. So what we're going to try to answer today is, how do we calculate this curve? How do we calculate this curve? And what this detection statistic here actually means. What is that? So where we begin is, this is a nice slide on this from Alan, and I'll just sort of reiterate it. So we begin with match filtering. So match filtering is the basis of this kind of analysis. There is a very small signal embedded in noise. In this case, I made a binary neutron star waveform. They're very hard to see in actual data. You have this embedded in some data, and then you convolve this with the template you're looking for, and you get some peak. And noticeably, you, of course, as Alan pointed out nicely, you're of course weighting by the power spectral density of the noise itself. Now, this is the basic model for what we're going to be doing, and the answer to what more is there is really just a lot more of this, and then careful checking. But we'll go through what some of those checks are. And, so first of all, we need to talk about the waveform models, because that's critical to actually being able to do this sort of match filtering. Is it relies on us having a good prediction of what all the signals we want to find actually look like beforehand. So this is a sort of a nice cartoon picture here. Well, this is actually real detector noise. This is 5914 again, sort of overlaid. And you can see it sort of breaks down into a few different periods. You have in spiral, you have the merger, and then you have the ring down. But how do we get that? Well, that comes from a few different places. Of course, we have numerical relativity, where people solve these very expensive, long-running computations and can actually tell us what these signals look like very accurately. They have some drawbacks. One of the main drawbacks is they're slow. So we can't generate many of them, and we can't generate many cycles of them. So we have a very broadband detector. We can detect many cycles of even binary black hole signals, and especially lower mass signals. But you can't necessarily generate a numerical relativity waveform for every single type of thing you might want to search for. So we have to use other things too. One of those things we use is a post-Newtonian expansion. This is, I think Alan showed a portion of it. I'm not going to go into that here. But that's a nice thing that tells us, it gives us a way to look at the early in-spiral of gravitational waveforms. And it's valid when you have V over C kind of small. And we do use this in practice. In fact, this was used in the detection of the binary neutron star merger that we announced back in October. So these things are very useful. But of course, the bread and butter is the models that come out of these things. So in addition to these, we take into account sort of analytic relativity, and then we combine these to make different, somewhat phenomenological models. These include, a couple different families, as we talked about. So there's families based on what the effective one-body approach, and also IMR phenom family of models. The important thing is to keep in mind that these are include some physical effects, but not necessarily all of them. So here's a general picture. Is what we're going to do is we're going to kind of figure out what effects we can try to search for. So this is a general picture. We have two compact objects. You can tell by the size that they're compact. You can't, but it's a picture. They're orbiting around each other, and each of these can have a different mass. So you have their two component masses, and each of them can have a spin. So they can spin along their own axis. And notably, what happens if you, for example, change the spin, you set them to 0, you get, of course, a different gravitational waveform. And one of the things I just want to note is of course, if you were to tilt these spin vectors and misalign them with the orbital angular momentum, you would get precession. We do not, at the current time, actually look for that physical effect, so we do make the assumption that the things we're looking for are, well, at least when we're searching for them, that are aligned with the orbital angular momentum. Now, that's obviously something we'll be looking to improve in the future, but that is what we're doing now, is we're looking for things that can be spinning, but they have to spin along the orbit of their angular momentum. So just to keep in mind, again, we're going to be restricting to where you have two component masses and just these two spin vectors. And of course, the cartoon picture points these going up. We do also allow them to be pointed downwards, just to clarify that. So then the question becomes, how do we build a bank of templates? Of course, what is a bank of templates? Bank of templates, essentially how we have to do this is, if we have one model, we can search for that with match filtering. We can look for peaks in the SNR time series, and then we can see how significant those peaks are. But we want to search for many different kinds of systems, which means that we need to search for every single one separately and then combine those together. And how do we do that? Well, first of all, what we do is we build what we call the template bank. And the general idea about these template banks is that they're designed to find a certain set of systems and not miss a certain number of them. So you can't have an infinitely dense template bank that would catch everything in this region, but that would be computationally intractable. So we have to allow for the loss of a certain number of systems, the loss of a certain amount of SNR. And we can, normally our requirement is that any kind of system that's within the boundaries of what we're trying to find, we lose no more than 10% of those kinds of systems. And what that tells you is how densely packed our bank of templates needs to be. And we can measure sort of how far templates are apart using what we call the match. This is an equation. Feel free to talk to me about it later. But essentially, it's a kind of inner product that tells us how close two waveforms are to each other. It does depend on the noise curve itself, but it will tell us how similar two waveforms are to each other, and that will tell us how we have to place them so we get the right density. So what physical effects are we going to include in our template bank? As I said, we'll include the masses of each object. We'll include a spin for each one that is aligned with the orbital angular momentum, no precession. And the other thing we'll do is, some things we're going to be emitting, notably, is we have no effects of matter. So when we say we search for binary neutron star systems, from a model perspective, we're searching for two low-mass black holes. We don't include the effects that the objects actually contain matter. That could be done, but we don't currently right now. We don't include precession. We don't include the fact that the orbit is might not be perfectly circular. Now, we do expect that most systems, by the time we observe them, will actually circularize on their own, because gravitational emission of very eccentric objects will tend to lend them to evolve to a circular orbit over time. But in principle, it might happen in some rare circumstance, and we don't search for that right now. Okay, so what we do search for. This roughly describes the region that we search for, and I just want to note that there's a couple ways that we actually build this. So we have a way to measure how similar waveforms are from each other. And one option that you can do is just to throw down random parameters until you get the kind of coverage that you want. So you sort of just put it in, check if it's already something too similar to it, and if there isn't, add it, and then just sort of repeat. You have this sort of iterative stochastic process you can build up a template bank. And in fact, that's what we do for most of the template bank. So here on the x-axis, we have component mass. This is in solar masses. So we're covering a region roughly from 1 up to a couple hundred solar masses in each component. And for most of the space, we are doing just a very straightforward brute force stochastic placement. Where approximations make sense, we can actually do what's called a geometric placement. That's essentially a place where we have enough knowledge about the waveform, enough knowledge to actually predict how closely overlapping waveforms are ahead of time, and we can develop an analytic metric. So we can place very efficiently here. But we've now placed our template bank. Maybe give you an idea of what we have done. These are actually all the templates. Now, you're not going to be able to see the difference in here. It's very high density of templates. So the orange here is the template bank that we used in our first observing run. It went up to 100 solar masses and down to 1 solar mass for each component object. For O2, we've extended that up higher to a few hundred solar masses. So we're now looking for much higher mass objects, also the ones down here. And I'll note that these template banks are actually public, so if people want to access them to see what sort of templates we're looking at, these are available. So now you have a very mechanistic picture. We have a template bank. We can use match filtering. You think, now maybe I'm basically done, and then I can draw this sort of picture like this, and then I'd get my answer, which is basically, okay, I have my set of detectors. I will use that to estimate what their noise curve is, and from that noise curve, I can figure out where I need to place templates. I generate a template bank. And now that I have my template bank, I can match filter each of those templates. I can look for peaks in the SNR time series. I can record where those peaks are and what the properties of those peaks are. And then, I do that for each detector, and then I can bring that together. I can compare those to each other. I can estimate what their significance is, and everything seems golden. We're done, right? Yeah, and in detail, this is easy parallelizable procedure. These are some science locks in Hanford and Livingston. Livingston this particular day had a very long, nice lock. Hanford had some interruptions. So this is very easy to parallelize. We can analyze huge chunks of time. We can split it up by data, estimate a different noise spectrum in each one, calculate an SNR time series. In practice, we run these on big computing clusters so that we can do these. And we can get that all done. We get all our results back, and we've made our detections, right? Well, unfortunately, no. If we were to do what I just outlined, unfortunately, we wouldn't be able to find anything and claim it with any significance. And the reason is things like this, not these, there's better probably examples. You probably should talk with Jess if you want a whole catalog of these sort of things, or actually go onto Gravity Spy nowadays and help out with that. There's huge catalogs of these sorts of things in the data. Every single one of these fools a match filter. And that's simply because they have a lot of power, and some of that power intersects the actual waveform. So I have an example of this. This is a blip glitch, as we mentioned in the prior talk. This black line is actually the time frequency trap of an actual binary black hole signal. This is a very high mass one. It's a very high mass ratio. But you can see that, okay, it kind of matches here. It doesn't match anywhere up here. A human would be able to tell that. A match filter can't. So unfortunately, our data is not in Gaussian. It has noise transients. So match filtering is not good enough, but it is a place to start. So where can we go from there? Well, the first thing you can do is listen to Jess's talk and remember back and look it up. And we can take into account what we know about the instrument and what's going on at the time to try to figure out what was going on in the detector and if there was something that should alert us that this data was be suspect. So for all of you guys who are looking into analyze LIGO's data, I would pay close attention to the Cat 1 and Cat 2 vetoes. I'm not going to talk much more about those. Again, I will throw it on to Jess if you'd like to talk with her about it. What I will talk to you about is what we can do in this analysis itself, because unfortunately these things do not remove everything. We're relatively conservative in what we like to put in those to make sure that we understand what's happening. So the analysis needs to often take care of everything else on its own. And we have a couple things that we can do. We have our sort of standard bag of tricks. Of course, the most powerful one is the fact that we require coincidence. So anything that we see must be seen by multiple observatories. In this case, Hanford and Livingston. And you can also then put some additional restrictions on that, just based on sort of astrophysical requirements. So if you have a real gravitational wave signal, it travels at the speed of light. It has to then travel between the sites, detectors, even if it's in a direct line between them, within 10 milliseconds, and any other angle less than that. And so you know that if you have two signals that are separated by more than that, they couldn't be the same. And you also have more information than that, because the instrument doesn't just measure some time. It also measures amplitudes and phases, and those can also tell you something. You can also look at how the actual morphology of the signal looks like. Is it consistent? Are the detectors actually seeing the same thing? And that's something you can look at. And if you have an actual model, as we do when we're looking for compact binary mergers, you can then ask, well, is what we're seeing in the data actually fit the model? And that's a huge suite of where our tests are. So one of the important things I said is the time delay. One of the other things you can do as well is actually look at the phase between the instruments. So our instruments are aligned such that a sort of general relativistic produced signal will have a particular phase relationship between the observatories. And that's a fairly generic thing. Here, I'll just demonstrate on this plot. So this is the time delay between detectors. As we said, it's roughly 10 milliseconds with some timing uncertainty. I However, you also have this phase difference between detectors. And you can see I've just plotted a couple of our example signals on here. So this is 5914. It's quite nicely lines up in exactly where you expect. This distribution here is what you'd expect from an astrophysical population of signals. And just to people who understand this, the noise is basically just uniformly distributed in the space. So noise can appear anywhere in this diagram. Signals will preferentially lie here. And of course, that is where we see our signals. This sort of technique actually was not used in our first observing run, but these signals were detected anyway, and of course, they're always detected there. So you can take into account that kind of information when you're trying to decide whether things are really consistent between the multiple observatories. What else can you do? Well, you can start looking at signal consistency tests. So this is in blue here, we have an SNR time series. This SNR time series has a particular shape to it if it is being slid across a signal in data. And you can predict what that shape is. It's just the autocorrelation function of your template sliding across itself. And then you can look at your SNR time series and ask, does the shape of that SNR time series actually match real signal? In this case, this is actually 5914, and of course it does match. This is actually a technique used by one of our flagship analyses called GSD-LAO to some success. And you can then use this as a discriminator to look between something that might be a glitch and doesn't really look like a signal and something that does. What's another technique you can use? Well, here's another example. This is actually a blip glitch in a slightly different time frequency picture. This is a standard sort of short time Fourier transform, not a Q transform. And you can see here in red, you can barely see, these are tracks of different waveform templates that are lining up with it. Now, the computer can't tell the difference, but a human can. And so you should have some ideas here for how you can exclude this kind of event if what you care about is finding things like this. So it should be clear that a real signal doesn't have any power at these frequencies. Okay, so one thing you can do is you can actually sort of target different kinds of glitches and simply look for excess power at, say, a set of frequencies, and then use that to kill these kinds of glitches. That's another technique that we use and is available for people to think about. So now I'm going to come to what I think is probably our most powerful technique. It's what's called, it's what's called normally the sort of Bruce Allen chi-squared, since he came up with it. Haven't come up with, honestly, a better name. But the basic idea is it's very similar to a kind of Pearson's chi-squared, but in bins. So normally it's done in the frequency domain, but just giving you a time domain picture to sort of conceptualize what's happening here. This is a time axis, this is strain, this is your gravitational waveform. And what happens here is that you essentially split it up into different bins, as you can see by the different color regions here. So I have, my first bin here, second bin here, third bin here, fourth, fifth, and then I can't hold the pen any more steady to select the other ones. And what happens here is you can ask the question is, if I have a signal that matches here, it should contribute a certain amount to my total SNR. Okay? And usually the way this works is we select our bins such that each of these bins should, in principle, contribute equally to our SNR. That's a choice, but it's the one we normally make. And so then you can ask the question is, do they actually contribute equally to the SNR? And so you can come up with this kind of chi-squared test that basically looks at the SNR contribution from each of these sub-portions of your template, and then looks for the difference between what you expect. And that turns out to be a very powerful technique. And before I go on, I just want to maybe refocus to a little bit on how we did this in 01. So I've gone over a number of possible techniques, and maybe I just want to emphasize the ones we used in the first observing run. So the first observing run, we didn't use all of these. What we did use is the chi-squared I just mentioned. We did require that a signal be observed by both LIGO observatories. We required that they be observed within 15 milliseconds. You notice I didn't say 10. That's because we allowed for some timing uncertainty in our actual procedure. That was probably a relatively conservative number, actually. And we required that it be observed by the same signal. And what we mean by that is we have this bank of templates. We search each detector with each one. If you have an SNR peak, it must be observed in both detectors. And it must have a peak in both detectors in that one template. If you have a peak in one part of the mask space and another peak in a different template, that didn't count. It had to be the same signal. Okay? So now, come back to this picture. It's a little bit more complicated now. So what you actually need to do is you generate your template bank. Of course, we have other preconditioning stages. Now, we do match filter. So we do match filter all the different portions of the template bank, and we calculate where the peaks are. We threshold on it to take the most significant ones. But now we also calculate our chi-square test, and in particular the Bruce Allen chi-square that I just showed. And then we perform a coincidence test. So we have different now what we call triggers. These represent peaks in the SNR time series. And we see, do they come from the same template? Do they occur within 15 milliseconds? That's our test. And then we can estimate our background. So that's the schematic view of what we did in the first observing run. So let me maybe say where we go from there. So how do we determine whether there's something significant or not? Well, the first thing we need to know is, what do we do with this chi-square test? I said we can use it to help discriminate. I didn't say how. Here's how. So just schematically here on the x-axis, this is signal to noise. So this is the value of signal to noise that we get from the analysis. And this is the value of our chi-square test. And we have a couple different distributions in here. So first, black. Black is what's coming from our background. And all of these colored ones here, these are injections. So these are software injections. We do lots of simulations to test how our analysis is doing. And of course, what we'd like to have is that these software signals are found with high significance and the background is rejected. And so the way this works is, you notice how this background here largely lines, and you can see some poking out up here, lines along contours of this dotted line. And so it's no accident that this dotted line is plotted like this. What we actually do then is we essentially say, okay, things like this have a high value of our chi-squared, which means they don't fit our signal that we expect to find very well. We're going to downrank them. And we're going to downrank them in such a way that matches this contour. So what that means is if the value of this chi-squared is close to 1, which means it matches well, we're going to give it a value that is just the SNR, just the signal to noise that we found it with. If we find it with a high value of chi-squared, it'll be given something lower. And of course, that's this equation here, but I'm not going to go into any more detail than that. But the basic idea is that we essentially reweight things based on the chi-squared, and this is what we call a reweighted SNR. And usually we use this sort of row hat notation. So in each detector, we look not just for SNR peaks, but we calculate this chi-squared value for each peak, see how well or the real signal fits that piece of data, and then we can reweight that based on this curve. Okay, and how well does this technique work? Well, here's an examination of 5914, just to show that this does not, in fact, affect any of the signals we found. So we have a couple curves going on here. In blue, we have SNR as a function of time. So this is what you get directly out of the output of the match filter for the best finding template. We also have our chi-squared time series. So this is the value of our statistic that we're looking to try to discriminate noise between signal. And you'll notice it has some interesting features. One is when at the peak of the SNR, it has a very low value, close to 1, which is what we would like for it to be a real signal. But you might ask why it has high values over here and here. And that's because this is very sensitive to the exact alignment of the signal. If you have something that is just out of phase between your template and the real signal, it will extremely heavily penalize that because its SNR contribution is extremely different because it's just canceling out. And so what you actually see happening is that you'll start getting effectively power that it can't be accounted for because it doesn't actually align. But so it'll get a very high value of the chi-squared until it sort of locks into place, as this thing perfectly aligns with the signal in the data. And so these are very typical, that you have a very low value here. And then in purple, we have our reweighted SNR. And you notice it basically agrees with the SNR and is, essentially agreeing with SNR time series pretty much everywhere. Here's just a time view of the triggers coming from different templates. So I was choosing a specific waveform template that rang off. Of course, many will respond to any given signal with different strength. And in this case, this is time, and this is the reweighted SNR. And you can see that in green here, we have the triggers from Livingston. So these are coming from different templates from our template bank. And we also have triggers from Hanford. So these are coming from different triggers in Hanford. And you can see that these are the ones that are actually coincident with each other with highest significance. And of course, they're the ones that are ring off most loudly, which is also consistent. Okay, so now the question is, how do we rank events? I have a peak in two detectors. I see that they're coincident with each other. Okay, that's a good test. But I now need to figure out a way to rank these events against how loud other things are in the data set and against anything I might have in my background. And so the way we generally do this is, of course, we will first look for coincidences. This is just sort of a cartoon picture of triggers that might be popping up in different detectors. Imagine this is from a single template. If they're within a certain time, okay, that's a coincident event. We're going to consider that some potential candidate. Now I need to assign it a number that I can rank it against everything else. So here's what we did in the first observing run, is our ranking statistic was just the network combination, so essentially the network sum of the two reweighted SNRs. So it's just each SNR squared, added together, and then we take the square root. So it's just, that's all it is. And that gives us a simple number. This is the number that on the plot I showed you a while back is the detection statistic. And now the only question is how do we calculate the background? Well,
sorry, what's the origin of the extra 5 milliseconds and the timing?
Yeah, so the 5 milliseconds, as I said, was probably too conservative. The thought behind it was that we wanted to allow for timing uncertainty in our own measurement of when the signal time was. So of course, physically, it can only happen within 10 milliseconds. However, what we're doing has a number, what we do when we actually analyze it is we find a peak in an SNR time series. That peak, because it's embedded, it's not entirely just signal, it's embedded in noise, can be in principle shifted by the noise. This is a fairly conservative overestimate of how much that can be shifted. So it's, in reality, it can be a lot lower, and in practice nowadays we don't use as much as that.
In principle, it's the width of the autocorrelation.
In principle, but it's in practice we chose something that was conservatively much larger than that width. But it was large enough to be sort of outside that bounds and a nice number, so we went with it. But nowadays we use something a little bit tighter that's more of like a distribution to try to better encapsulate that. But we were fairly conservative in the first observing run. So now the question is, how do we calculate our background? Well, here's our data. Here we don't have any coincidences, at least in this particular segment of time. But there's another way I can create data, at least a sort of fake facsimile to the data, which is just to shift, just to shift the triggers in one detector relative to the other one and create a new data set. And so what we do is we shift, say, the Livingston detectors by an increment of, say, 100 milliseconds, so something much greater than the light travel time. So anything that's found in coincidence here is not astrophysical by the same requirements as in our standard analysis. And we get an entirely separate set of triggers that is generated in exactly the same way. So everything in our background has exactly the same properties as everything generated for our search, but it will have different combinations of the noise. And we can repeatedly do this, so we can shift this again and again and create a new background set. And then we can collect after we do this all the possible times, we get an entire background set that could in principle last for tens of thousands or hundred thousands of effective years. And that is how we collect our background. And then what we do is we compare that to what's in our search. So coming back to this plot, I hope people now have some idea of what this detection statistic is. So in principle, that's just a network SNR, except it's downranked by how badly it performs in this chi-square test. On the vertical axis, we have number of events. And you can see that this is our background here in black, extending out. And here's when we actually do the analysis, is we get one event where we expect extremely few. There's one feature of this that I'll emphasize now, which is what is this purple curve here? So this tail here is entirely caused by our actual signal matching up in random coincidence with things in the other detector as we shift the data around. So in fact, this tail itself, if we collect more and more data, would start going down, assuming there aren't real glitches that look like this in a longer view of the data. So that's where I'd like to leave you, except for one more thought, which someone should ask, which is how do we know that this search actually finds anything? One of the ways we know is because we inject lots of simulated signals all the time. Every single time we run an analysis, Alan nicely introduced this concept. We have an idea of what's called a closed box. We do an analysis. We don't look at the result, but we do look at diagnostic tests performed in parallel of the same data, which is one of those tests is we inject lots and lots of simulated signals and see if our analysis can find them. And that's what this is basically a summary of, which is here's what's called chirp mass. This is a measure of mass of the system. We have what we call decisive optimal SNR. That's the signal to noise in the least sensitive instrument. But the basic point is that very loud things, which are up here, are all found at very high significance. These are in blue. Things in red, we missed. They're too quiet for us to find, or we missed them for some other reason. And then you have this region in between, which are found sort of marginally well. And so we do these sort of tests with many different simulated populations every time we analyze new data. So this is a constant sort of test we do to ensure that we understand exactly what our analysis is doing, how well it's recovering signals, and in principle, if there's something odd going on that we're missing, we can understand why we're missing it. And with that, I will actually ask for questions if there are any.